Thank you very much for the kind introduction. Thank you very much, the organizer, for the invitation to this really wonderful and broad spectrum program. Let's. I'm a little bit scared of the pointer. Okay. Let's go on. It's okay. So I would like to start with the acknowledgements instead of leaving them at the end. Okay, I'm a theorist, but I'm very lucky because I've been working with a fantastic experimental group in Pavia. These are the main leaders, Matteo Galli and Daniele Baglioni. New faculties are joined. And of course, I want to thank also my mentor, John Saip. And of course, we know that most of the work is done by the PhD student. And here are listed only those that are currently in the group, but the ... means there are many others that are not listed here. And we have many collaboration, but I highlighted here the collaboration that contributed specifically to the work I'm going to show today. Okay, so this is the outline of my talk. I will start with a brief introduction, just to be on the same page. And then I will talk about recent research. And then in the spirit of the workshop, I will try to see whether we can say anything about new trends in quantum nonlinear photonics. Of course, these are opinion given on my expertise and my work, but new trends, of course, can be given also by other people. Okay, so let's start with the introduction. And so for the people that are not familiar, just a few words about squeezing. So what's squeezing? So for a theorist, squeezing is like this. So it is a squeeze vacuum state. And but if you want something more, let's say, more physical, you can try to measure the electric field of squeezed light. This is vacuum squeeze state, so the average value of the electric field is 0, but the variance of the measurements depends on the phase of the electric field, which and you can get this image, for example, with the homodyne detection. What is nice is that you can see that the phase, the variance decreases and is as a minimum in some points, and this minimum is actually, oops, I'm trying to see that. This minimum is actually that's a lot of slides. So this minimum is actually smaller than shot noise, which is the same measurements done on vacuum. And that's why we call it squeeze, okay? Squeezed light, squeezed vacuum in particular. And we typically measure squeezing by taking the ratio of the variances and putting logs scale, okay? So as you can see here, from the state I wrote, in order to get squeezing, you have two creation or annihilation operator involved, okay? And so there are two phenomena that are typically used to get squeezing. One is a spontaneous parametric down conversion. This is a second order nonlinear phenomena. This is the Hamiltonian. And the other one is, it's coming? No, yeah, it was coming. Okay, spontaneous four-way mixing. And again, this is a third order nonlinear phenomenon. They're both used for several reasons. First of all, because in the dipolar approximation, the chi2 of material is vanishing in centrosymmetric material or amorphous material. And so there are some cases in which you can simply not use spontaneous parametric down conversion. And while in that case, you can always rely on spontaneous four mixing. Now, beside the Voltan celebration, this year we celebrate also 40 years from the first observation of squeezing, okay? And this is the squeezing. This is actually, you see the measurements with the variance that goes a little bit below the shot noise was 0.667 dB of squeezing, and was done not with chi2, but with chi3 in spontaneous four mixing in sodium vapor, okay? 1 year later, Jeff Kim will show that you could also do that with SPDC. In lithium niobate. It was a big quark crystal in a cavity, but was a lithium niobate, who is becoming very popular today. And then another important step was in 2016, where people worked very, very hard to measure, I think still today, the largest value of squeezing ever reported, 15 dBs of squeezing. That's a huge number, okay? Now, this is bulk. What has been done with integrated photonics? So many people contributed. Here I'm listing what I believe is probably, to my knowledge, the first example in which people start to observe spontaneous four mixing in waveguides and ring resonator in silicon. This is a group in Ghent, and this is the first of the Clemens, who show that if you shine strong enough light at 1550, 1540 in this case, the light, the pump has been removed here, you can see two big signal and other generated by spontaneous four mixing. They didn't check whether they were with coincidences that were really generated in pairs, but of course, this is actually the case. Then I want to mention two work from our group. One is in 2015. We show the generation of energy entangled photon pairs. I think the first generation in a silicon chip, in a silicon ring resonator. And we also perform the measurements, or actually my colleague performed the measurements with Fresnel interferometer, and we prove entanglement. And then another important milestone, I believe, is in 2021. This is a work I did in collaboration with Xena, the Quantum Technologies. And this is a is a squeezer, in fact. They measure 8.3 dB of squeezing out of this object, okay, which is remarkable. And if you think about it, if you look at the power and the dimension in this experiment and the dimension of the device in this experiment, you wonder, how is that possible? Because these are very, very tiny devices, okay? Now, this is a general principle in light and matter interaction. So in order to understand that, the best example is taking an elevator, considering two people in an elevator, one is light and the other is matter, or vice versa, whatever you like. And we don't know anything about these people. We don't know their mood, whether they're happy or not. But I can tell you one thing, the probability of interaction would be directly proportional to the time spent in the elevator and inversely proportional to the size of the elevator, right? So if you stack two people in an Italian elevator for 24 hours, no matter who they are, they're going to interact, okay? And so this happens exactly, but really exactly with light and matter, because if you create a resonator, you increase the electromagnetic density, the energy density, and this is proportional to the time light is confined inside. This will boost interaction, and the density of the energy is inversely proportional exactly to the size, the mode volume of the elevator, okay? Now, the nice things with nonlinear optics is that since these are nonlinear effect in the electric field, you have this effect to a certain power, right? Because if we have a field enhancement of 30, for example, and you take something which depends on the 8th power of the electric field, you will have an enhancement of more than 8 orders of magnitude. And in fact, in spontaneous form mixing in integrated device, the enhancement is typically between 10 to the 8 and 10 to the 10, which are a number that almost belongs to astrophysics, okay? Okay, so this was a kind of introduction. And but I want to convince you that it's not just making stuff small to have something to bring around or just to increase efficiency, okay? Now we are at the stage of technological innovation, which allow us to exploit integrated photonics to do more than that, okay? And I will show you two examples. The first example, this with reconfigurable sources of non-classical light, and in particular is connected to the concept of an entangled frequency bin. What are entangled frequency bin? We can encode quantum information in many degrees of freedom. One in particular are frequency bin where photons are. And this can be done relatively easy with a ring resonator because you have kind of bins that are associated with the resonant frequencies of the ring resonator. And if you pump a ring resonator, because of energy conservation, photons will be automatically generated and in correlated bits. And in fact, you get a state which is essentially given by this, okay? And so it's an entangled state, and it is a coherent superposition of the pair being generated in symmetric bins with respect to the top, okay? And this was highlighted very well by two groups in particular, the group of Roberto Morandotti in INRS and the group of Annie Weiner at Purdue. And then we recently reviewed a number of results about this because frequency bin itself, they date back in the 90s, okay? These are work done in integrated photonics, okay? But now, if you think about one single ring, well, this is pretty much the kind of state you can create. You cannot really customize that much what you are creating, okay? So we wanted to do more, taking advantage of integrated photonics. And so a few years ago now, John and I ended up with this idea, which is actually inspired by a box system, which is called the sandwich source. In a sandwich source for entangled photons, basically you have two crystals which are oriented perpendicularly, and then you pump both crystals at the same time, and the coherent superposition of the pumping results in a coherent superposition of the emitted photons, typically entangled in polarization. So now we decide to do the same in an integrated device by taking ring 1, ring A, and ring B. And so by creating a simple Mach Zehnder, some filters to redirect the pump, we can create a state of the two photons that is a coherent superposition of the state that would be generated here and the state that would be generated here. And the nice thing is that by tuning the voltages here, we can weight these coefficients in the imaginary part, in the phase and in the amplitude. So we can work and construct this kind of state on demand. We didn't do just theory, because then we asked our colleague in the experiment. This is a collaboration with CLAT in Grenoble, and we fabricate actually the sample. And these are some typical experimental value. The Q-loaded was 150K, the free spectral range 700 gigahertz, the radius 30 microns, and so on. And then, in fact, my colleagues measure them, and we have been able to obtain the quantum state tomography of each state that can be controlled by changing the voltage that is applied. So we can reconfigure to create a very, very simple two-photon states, or of course another 1-1-1, or all the Bell states. Okay, and I want to point out that despite this is an integrated system, the fidelity was up to 90.2%. So we have good control of what we're generating, and the purity 99.9%. Okay. In particular, another experiment we performed was to set the device to create a Bell state, and we violate CSH inequality by 140 standard deviation. Okay, this is raw data, no background subtraction. Okay, and this is a number which is challenging also for a bulk experiment. Okay, and we did it in an integrated device. So we were very happy, and then the nice thing is that with integrated photonics you can scale this idea, and so you can go beyond qubits. You can take more rings and create qubits, for example, and qubits, another example. And again, these are not simulation; these are measurements. Okay, so we have enough light, and the nice thing is also that we can keep the efficiency, the rate generation, pretty much the same, because basically we have the generation scales with the square of the number of the ring. Okay, but then at a certain moment you have to keep the generation rate sufficiently low to avoid multiple pair generation. Okay, but this is our experiment. Then, of course, we decided also to use integrated photonics to go not only beyond qubits, but also beyond photon pairs. Okay, and so we started doing 4-photon experiments, and these I don't enter in the details because I don't have enough time. Basically, we did Gaussian Boson sampling, and we tried to recognize different graphs using basically boson sampling, which is one of the application is graph recognition. And if you're interested, you can read in some more details in this recent work. Not only beyond photon pairs, but we also wanted to go beyond squeezing. And so trying to see whether integrated photonics could be used to generate more states, Gaussian states, like, for example, JZ states or W states. And these are theoretical work that we have been doing in collaboration with John Sipe. Melissa Banich was a former PhD student of John. And we design samples to generate this kind of non-Gaussian state. And now we are, in fact, working to implement that on a real platform. Okay? So we have some flavor of what can be done in spontaneous form mixing in an integrated device for non-classical light. The second example is a work we did on a spontaneous parametric down conversion. Okay? And in particular, in linearly uncoupled resonator. And I will try to explain you why we decided to work on this idea. So, despite the second order nonlinear response can be pretty strong, okay, you may believe that second order nonlinearity is very appealing. okay, for a number of reasons. Okay, is very strong, so it's more efficient. The pump filtering is very easy because you have a pump at 2 omega and your light generated the fundamental frequency. While in spontaneous form mix, the pump is typically in the middle or nearby. So filtering is a huge problem and a headache. And finally, you get rid of several nonlinear parasitic processes that you have in spontaneous form mixing, for example, RAM scattering. Okay? But if you look at the literature and you try to look for the example in which there has been a resonant second harmonic generation or SPDC in an integrated device, you find very few examples. Okay, one of them is, for example, in aluminum nitride in the group of Ontang at Yale, and the other one is a very recent results by the group of Kerry Vahalak at Caltech, in which they exploit Ki2 in silicon nitride. Silicon nitride doesn't have a dipolar Ki2 unless you can kind of polling it using photogalvanic effect. This is something that has been extensively studied by Camille Press at the PFL. Okay, so you can have a Ki2 also in silicon nitride. But these are, I would say, pretty much what you find about resonant SPDC. And why is that? The problem is that because you work in a wide spectral range, you have to optimize your device, your integrated device, at 2 different wavelength range. And you have to be sure that this works on a sufficiently broad range because the device is never going to be fabricated as you want. Okay, because there is fabrication defect. And so you pull one thing, so you lose another. So in Italian, we say that the blanket is too short. That's the problem here, okay? And so we try to find a solution, which is probably obvious. If the blanket is too short, you can use 2 blankets. That's the thing. And we did exactly this. And we are basically leveraging on the concept of linearly uncoupled resonator. So we took 2 resonator, crazy. So resonator 1, okay, and we took resonator 2, okay? And then what happens? We create something that is a device in the middle, which is an uncoupler. What does it mean? That if light is in the resonator 1, it's redirected to resonator 1, and if light is in resonator 2, it stays in the resonator 2. This is an advantage because if I by chance put a tuner on resonator 2 and I move the spectrum, nothing will happen at the other spectrum because the light of resonator 1 doesn't circulate in resonator 2, doesn't see the tuner. Okay? Of course, the easiest way to uncouple to resonator is put one in common, the other in pavia, but there is no use of that. Okay? So the problem is that you want linearly uncoupled resonator, but still you want non-linearly coupled resonator. Okay, so you can have this integral is equal to 0, but this integral can be absolutely different from 0. And so you pay a price, the nonlinear interaction occurs only in this uncoupler region, okay? But at the same time, you have flexibility in tuning the linear properties, okay? George Stegeman used to say that if you want to do good nonlinear optics, you have to do fantastic linear optics. That's the trick. First is the linear optics, and then you have the nonlinear. Okay, and so this is a work that initially was suggested for spontaneous form mixing, and then and we passed it to flexibility because it's relevant for squeezing, and then we started to investigate it in Ki2. And now I use this because it's scary. Okay, so one possibility to obtain a linearly uncoupled resonate, 2 linear uncoupled resonate is using a Mach Zehnder. If you have a dephase of pi between equally balanced arms, basically light that travels here intercellular is redirected back here, and the other one is redirected back there. Okay, and if you take this, and this happened for any splitter, 50, 50, 60, 90, 10, 80, 20, still with pi you will always have uncoupling. And of course, if you design your coupler such that you have a superposition in some region, and we consider lithium niobate, and we also pole to achieve a phase matching here, okay? Then you can have a nonlinear interaction, okay? This is not a real device, this is a theoretical calculation, but what I'm proud of my student is that we really did consider everything, every dispersion of the refractive index, the optical elements, the coupler, the Mach Zehnder. So I bet that when this is realized, this is work exactly as we predicted. And these are the results. Yeah, Okay, these are the results. So the generation rate is on the order of megahertz per milliwatt, okay, which is about 10, 20 times more than in a silicon ring resonator with a distant Q. Okay, but then the nice thing though is that when I change the phases of one resonator with respect to the other, I can rearrange the resonances where I want. And so this device works on a 300 nanometer bandwidth. It's huge. It's huge because still here, you still have, let's say here, for example, still a decent rate, okay? And this is something that is due to the fact that the nonlinear interaction occurs only in the arm. So you need a coherence length that is longer only of the arm. While in a ring resonator, you need a coherence length which is longer than the path traveled by both fields in the ring, okay? So when you have a very high quality factor, in a ring resonator, you need phase matching, basically phase matching, okay? Here we don't have phase matching because the delta K is different from 0. We don't care. The coherence length is still longer than the part that has been poled, okay? Very good. This is theory, but we have some hint that this might work because I collaborate with Camille Brass, the PFL, and since they were working on photogalvanic, I asked them to fabricate two linear length coupled resonator, okay? And you can see the two resonator here and the Mach-Zehnder. And then they poled the resonator. In particular, they poled the upper arm of the Mach-Zehnder. This is a 2-photon image. You can see that this is poled. Here is poled. There is Sky 2, okay? While here is not. In the bottom part, there is not. Why? Because the light of omega and 2 omega circulate only here, okay? So this is precisely the device I mentioned you before, but in silicon nitride, okay? Now, we didn't try spontaneous parametric Young conversion yet, but we tried second harmonic generation, okay? And we were able to generate, to obtain a very good conversion efficiency over a very large bandwidth. And in fact, if you look at the paper there, you will see that we have been able also to generate a frequency comb by spontaneous forward mixing in one ring and double it entirely at the second harmonic and exiting on the upper ring. Okay, so it's very interesting. It's almost a little lab, okay, despite the fact that you have a huge lab to send the light in, but it's still it's very complex. Okay, so from these two examples, I want to try to see whether we can get some ideas about the new trend that we are having now in the linear quantum photonics. So the first thing, I think that we can see that we are moving beyond squeeze state, definitely. People are now, they know how to do squeezing. And now they are trying to move and create more complicated states. Basically, not inventing anything because most of the job has already been explained and done by Marco. Basically, Marco did in bulk what people are trying now to do integrated at any level, okay? And this is a work that has been published very, very recently by Xanadu, okay? These are the photonic molecule I have been showing you before. And by making interfere the squeezing from these 4 photonics molecule, a unitary, and getting these 3 outputs, then they send 3 of these outputs in a photon number resolving detector. And when you have a double click, when you have 2 photons from each of these 2 ports, what they generate is a Gottesman Kita F Preskill GKP short state. Okay, this is why this is very important, because this is a state that can allow you fault tolerant quantum computing. And so this is an important step for photonic quantum computing. And this is something that is very, very difficult to generate in bulk. So this is done in integrated optics. I can tell you that from here to the detector, the loss are only 0.8 dB, which is amazing, okay? Because of course, loss is the only thing you would sell anything you have to compensate in quantum optics. The only things you cannot compensate, okay? So they're working hard to reduce the loss. So this is the first trend, beyond squeeze, okay? And we can do that in integrated photonics. Second thing is that new material are getting ready, okay? So CMOS compatible material dominates integrated quantum nonlinear photonics, in part because, of course, CMOS are interesting for many applications. They leverage on fabs and so on and so on. But of course, also because spontaneous forward mixing, as we mentioned before, is very easy to design an integrated device in a small wavelength range of operation. Okay. Now new materials are getting ready. There have been example of generation of photon pairs in relatively complex integrated device in many material, gas, in-gap, aluminum nitride, and so on. Perfect, I'm almost done. And then now also thin film lithium niobate is getting very, very, very high quality integrated photonics. There are some challenges with the thin film lithium niobate, but it's a very promising material. This is certainly a trend that we're going to see in the next 5-10 years for sure. New materials beyond CMOS. Okay, and the third is also the revival, if you can, of second order nonlinearity. Why? Because at the beginning of quantum optics in integrated device, people naturally search for SPDC. Okay, and an example, of course, again, John Sy, who worked basically in anything I know, propose the use of algas and angular phase matching to generate PET. This was a theoretical proposal, okay? And angular phase matching now start to be investigated also experimentally, okay? So nowadays, as we have seen here in the show, in what I told you, we are finding even new ways to use second order nonlinear processes. Again, to get all these benefits in handling the pump, which is very, very strong, and yet get our quantum signal. Consider that in spontaneous phone mixing, you have to filter between 100 and 120 dB your pump. So it's a lot of filtering. And of course, you have a lot of loss because of the filters. Okay, and of course, you cannot tolerate that. Okay, so this might be a solution. And I think that with this, I give you all the message I wanted to give you. And so if you have any question, I'm happy to answer.